Hi folks, welcome to a video about interactions. So, people in my classes have been investigating what happens when objects interact. And there are two basic cases that a lot of folks looked at. Case one we'll call a hit and stick, and case two we'll call an explosion. In the hit and stick, here's a very simple case, what we're calling case one. We've got a cart of mass m that collides with another stationary cart, also of mass m, and this line here I'm using to denote or delineate two instants, or to differentiate between two instants, and those instants are before the carts interact and after the carts interact. Now, I asked my students to sort of play with some actual physical carts and devices that measure speeds. And I also asked them to use some intuition and sort of maybe guess what they thought would happen. And a lot of folks correctly will guess that this system ends up at a speed v over 2. Those two things are stuck together. And again, this is as compared to that initial speed v. All right. In a case like this explosion, these two carts start together, and I'll make a special note of with a speed of 0. And then this spring-loaded plunger is engaged. The two carts push off of each other, and well, what ends up happening again, and intuition can probably bear this out, is this one. If this one moves at a speed v, then this one moves at a speed v over 3. All right, so the question is, what is it that's constant over time? What is this? What combination of m's and v's yields the same total both before and after an interaction? And saying what's constant over time, that's the same thing as saying what's conserved. My students approach this exercise with the idea of defining a quantity that's conserved when objects interact, because conservation laws are some of the most fundamental laws that dictate how the universe works. So what is it that's the same? Well, notice we've got in the beginning here, if we look at the product, hang on one sec here, let me try this. The product, okay, of m and v in the beginning, well, that's not good. If we look at the product of m and v in the beginning, well, this object has a mass m and a speed v, and this object has a mass m and a v of 0. I didn't explicitly state that before, but that's the implication here, that that cart was stationary. In the end, what we have is, well, each of these carts moving at that speed, v over 2. And what we get is, well, over here we get a total mv, and in the end we get mv over 2 plus mv over 2. That's a half of mv plus another half of mv, and what we get is the same total. And what that leads us to is the fact that, I mean, you know, sort of our intuition told us this, but what people have a hard time, or you know, some brand new physics kids have a hard time with, is the idea of, well, my intuition, you know, tells me what probably happens, but what does that mean about the actual definition of quantities? Well, I am telling you the answer is there's this quantity that's the product of an object's mass and velocity. And if we look at the sum of all those products at any instant, here's one of them, here's a second one in the beginning, here's one of them, here's a second one in the end, the sums of those products are always the same. It means that that product is a conserved quantity. And that product is called momentum. All right, and that product, momentum, we use a variable p, lowercase p, and by definition, momentum is the product of mass and velocity. Yeah, I'm still here, I'm just thinking. So if we look at this second case, case 2, In the beginning, we've got, well, each object moving at velocity with velocity 0, we've got a total initial momentum of 0. And in the end, well, if momentum's conserved, we better get a momentum of 0. Well, this one has a momentum of m times v to the left. This one has a momentum of 3m times v over 3. Well, check this out. And those 3's can go. So look, we get, these each have momentum m times v. We want momentum to be conserved. The only way that can be the case is if we did mv minus mv. Okay, so what if we did this? Let's say that this one's negative and this one's, so this one we're assigning a negative momentum. This one we're assigning a positive momentum. And yeah, then we get what we want, that the initial momentum, 0, equals the final momentum of 0, and momentum's allowed to be conserved. Now, I'm going to make a special bit of notation here. I'll put a little arrow over the momentum and the velocity, and that's because momentum and velocity are what are called vectors. They're vector quantities. And in a vector quantity, direction is of real significance. It matters. And in this case, since we're limiting things to moving in only one dimension, what we're saying is, I hereby say that this is the positive direction, that is the negative direction. All right, and then we have to take into account the direction that things move. And we do that, we take that direction into account by quite literally explicitly saying that momentums can be positive or negative, depending on the direction that the objects are moving. All right, and this also says, you know, since v is a vector and so is p, well, these vectors are always in the same direction. Whatever direction an object moves, that's the direction its momentum is in. Now, as a bit of note-taking advice, if you see me write something down, you probably write it down. All well and good. If there are words that I'm saying and not writing down, that doesn't mean they're not important. The act of note-taking is one where you have to decide if things are important or not, and therefore write them down. So don't be a robot and simply only copy down what is written down for you. Be an interpreter. Okay, decide what's important. Now, let's look at another case. All right, we've got two objects, each of which are moving. And let's say that through however it happens, but these two objects hit and stick. Now, here's what we're going to do. I'm going to formalize and say, you know, the way that you approach this situation, right, when objects interact, if you're a physics person, what you do is you apply the fact that momentum is conserved. All right, and I'm going to do that, you know, at its sort of most fundamental. I'm going to do it like this. I'm going to use some symbols. And say that. All right, now what does that mean? This part means sum of all. So this term on the left says the sum of all the initial momentums. This term on the right says the sum of all the final momentums. That is as fundamental a way as you can do to say momentum is conserved. Add up all the momentums at one instant and add up all the momentums at a different instant, and that has to yield the same amount. That has to be the same, because that's what being conserved means. Now, what you then can say is we have two objects. So what we can say is, let's look at the first one's initial momentum. Let's look at the second one's initial momentum. That's got to be equal to the sum of the first one's momentum afterwards and the second one's momentum afterwards. Right? And we can do this if we want, which says, remember, we have to take the fact that momentum's a vector and things maybe move in different directions, and we have to be able to account for that mathematically. Okay, and then, well, how do you do the first one's initial momentum? Well, momentum by definition is m times v. So the first one's initial is m1 and v1 initially. And the second one is m2, v2 initially. And this one is m1, v1 afterwards, final, plus m2, v2 final. And if we want, we can say, well, it's the velocities that are the vectors now. Were I you and I was solving a problem, I wouldn't start here or I wouldn't start here. I would start here. How am I going to remember 1 and 2 and initial and final? Well, that's why you're in AP Physics. So now, what can we say? Whoops, we don't need that. We can say, here's what I know. I know, let's decide to call this object 1. Let's decide to call this object 2. Let's decide to call that the positive direction and the negative direction. Okay, well now we know all this stuff. All right, so this is 1,500 times 24. What's that? 36,000. That's 36,000. And the units must be these units times these units. Kilogram meters per second. Now, you can say plus and make the velocity negative, or what you can say is, well, minus, because object 2 is moving in the negative direction, 45 times 8. That's the same as 9 times, wait a minute, isn't that also 36,000? It is. It is, right? I think it is. Yeah, it is. So look at this. The system's initial momentum is 0. These are two objects that are moving, but they move with what we call equal and opposite momenta. Momenta is the plural of momentum. All right, so this says that in the end, now check it out. We have just defined, because I say so, hey, what if these two things were to hit and stick together? Well, hit and stick allows us to say, well, the two final velocities will be the same thing. So that means that we can end up writing this for this special case as, here's the two things stuck together moving at some final velocity. That's only if they hit and stick. Really what we're saying is, forget about calling it V1 and V2 final, just call it V final and V final. And then we've got M1 V final plus M2 V final. Algebraically, that's the same as this. All right, so, well, you know, if you want, we can say M1 plus M2 is 6,000 kilograms times V final. Well, I guess who cares? The only way for this to be true is, well, yeah, V final must be 0. If these two things happen to stick together and have to have a total momentum of 0, because they did in the beginning, they better now, that means the system can't move at the end when they're stuck together. Okay? Okay. What if the truck ends up bouncing backwards? Bouncing back to the east. Well, let's start with our sort of baseline expression of momentum conservation. That says M1 V1 initial plus M2 V2 initial is M1 V1 final plus M2 V2 final. Well, the initial part hasn't changed. This is still, this is still 0. There's still 0 initial momentum. Now what we're saying is the truck, remember that's number 2, moves east at 2 meters per second. The question is, that means we must be able to figure out what happens to number 1, the car. So I'm going to say M1 V1 final. Now look, moves east at the end. That means that's a positive final momentum. If we say that this way is the positive direction, this way is negative. So this saying east translates to this object's momentum actually being positive. So we can say this is, let's see, 2 meters per second times that 45. That's 9,000 kilogram meters per second. All right, so watch this. And that means M1 V1 final is negative 9,000 kilogram meters per second. Algebraically, I subtracted this from both sides. And that means that, look, we can find V1 final. It's negative 9,000 divided by 1,500. That's M1. So that's 90 divided by 15, that's 6. Yeah. But furthermore, it's negative 6. And what that means, if we were to translate that and maybe use some words, right? I would say what this really means is V1 final is 6 meters per second west. How do I know it's west? Well, look, the velocity is negative. So we can tell a lot about what happens in the end to one thing if we know what happens to the other thing. So this form of an equation can be very, or is very useful when investigating or interpreting what happens when objects interact. Okay? Here's a simpler, well, maybe not simpler, but this one at least doesn't have any numbers. Let's assume these two things hit and stick, and let's look for the system's final velocity. Okay, well, let's see. If we say M1, V1 initial, yeah, this might be a little bit redundant to do this. M1, V1 final. You might just jump right into a solution, but it's never bad to baseline yourself with, here's what I'm doing. All right, now I'll call this 1, I'll call this 2. All right, I've got to be careful about direction. These things move in opposite directions. M1, V1 initial is M times 2V, same as 2MV. Initially, look, object 2 moves left, 3MV, right? 3MV. So the system's initial momentum is negative MV. Guess what? The system's momentum ever is always MV. Negative MV, I should say. All right, now, when we say hit and stick, remember what that allows us to do is say we are defining the fact that these two things stick together as a single object and move with a final speed. So I can say, well, what's M1 plus M2? M1 plus M2 is 4M. V final. And look what doesn't matter. What actually doesn't matter at all is what the masses are, because this factor of M goes away. And what we get is that V final is negative V over 4. Or, translating into words, V final is V over 4 to the left. How do we know to the left? The sign of our answer tells you so. Notice we made the choice here without too explicitly saying, and it's probably a pretty darn good idea to say, here is what I define as my directional system, right? This is really a positive 2MV. This one is negative 3MV. All right, so what does V over 4 mean? It means that no matter what this speed is, if these two masses have a ratio of 3 to 1, and they're moving with the speeds shown and the directions shown, that in the end, the system will move in the direction of the more massive one initially, but at a quarter of that one's initial speed. Okay? You are hereby an analyst of momentum conservation situations. What you must be able to do are a few things. You must be able to employ that expression. You got to know what it means. Maybe I'll do this. Vector, 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 vector. And when I put those vector things in there, that means, okay, these might, turn into, there might be really positives or negatives here in each one of these to indicate direction. Okay, you got to know what that means. You got to know that m times v is momentum. You got to know that m1 v1 initial, for example, is the first one's initial momentum. And you got to know that, like this side of this equation is the system's total initial momentum. And this other side of the equation is the system's total final momentum. All right, so we exhaustively and extra thoroughly did that here. Right, we're saying momentum is conserved. Momentum of what? Well, of everything. Add them all up. When? Well, before anything happens. Add them all up. Here's how you do it. The first ones plus the second ones. How do you do momentum? M times V. All right? If you wanted to be, really explicit, you would say M times V is 1,500 kilograms times 24 meters per second. I did that in my head and wrote 36,000. Okay, you have to know that in some cases, like specifically hit and stick collision, that the final momentum can be expressed as the two things together moving at a common final velocity. Not everything's a hit and stick, of course, so you have to be able to sometimes keep those final terms separate. And with that in mind, perhaps, like we do here, find something unknown. This is a real important step. You have to be able to interpret your answer. You really have to be able to include and account for sign difference. All right, being able to interpret signs of answer, S-I-G-N, positive or negative, is a big skill. Okay? And, you have to be able to handle things that aren't always entirely, numerical, but still quantitative. All right, when I see you next, I will ask you a question that is sort of like these. And then we'll get lots more practice with momentum conservation examples. Okay? Okay. Fare thee well.